Hi, in this video, I'll be solving the free response questions from the AP Stats exam of this year, 2022. I'm an AP Stat reader, meaning I grade AP statistics. I've been a reader for about 5 or 6 years now, so I think I've got the system kind of down. But I actually teach in college. I don't teach AP. So I would appreciate any feedback or comments from people who are involved in AP statistics more intimately year-round. So please put them in the comments below. All right, let's go now. Question 1. A biologist gathered data on the length in millimeters, mm, and the mass in grams for 11 bullfrogs. The data shown in this plot. The question says, based on the scatter plot, describe the relationship between mass and length in context. In AP statistics, when they say the word in context, what they mean is the scenario that they're giving you. They expect that in your answer. So for example, this whole thing is about the mass and length of bullfrogs. Then say the words mass, length, and bullfrogs in your answer. Use words that reflect whatever variable we're working with. So the variables here are the length and mass, then use the word length and the word mass. Use words to describe whatever population we're working with. Here, the population are the bullfrogs. Use words to reflect what sample we're working with. The sample here is the 11 bullfrogs. So anything involving population, sample, variables, parameters, use words, and that's what they mean by the word in context. They want to describe the relationship, so here it is. It's a linear relationship. So I would say the relationship is there is a strong. In real life, when you have a line that fits so well like this, you are extremely happy. But on an exam, if you don't feel confident enough to say the word strong, you can temper it by saying something like moderately strong, for example. Positive linear relationship between the two variables, between x and y. And x here is the length, and y is the mass of the 11 bullfrogs. On the AP exam, when you're describing a scatter plot, they want to see the strength, the direction, positive or negative, and the shape, either linear or nonlinear. Now, if there's an outlier, you need to identify the outlier. Well, in this case, there isn't any outlier. Well, in real life, when there's no outlier, just ignore it, just move on. On the AP exam, it's safer to actually say it out loud, to say that there's no outlier. So here I have comma with no outliers. One more point I want to make is in describing the scatter plot without doing inferential statistics, you can only say things about what you see. And what you see are data about the 11 bullfrogs, about the sample. You don't know anything about the population of all bullfrogs. So if you don't have the number 11 there, it would be wrong. Now, whether the rubric for this question will penalize you for not putting the number 11 in there, I don't know. We'll wait and see. Now, continuing on. From the data, the biologist calculated the least square regression line, that's the solid line there, for predicting mass from length. The least square regression line is shown in plot 2. And here it is, predicted mass is equal to that equation. Identify and interpret the slope of the least square regression line in context. Again, the word context means you must use words for the variables and the sample or population as the case may be. Here's the variable x. Here's the dependent variable y, the predicted dependent variable y hat. So that makes this the slope. First they said to identify, and then they say to interpret. First we identify slope equals 6.086. And now interpret it. The slope of a line, any line, means the change in y for every x of 1 in x. So we just plug in the verbal context for the x and y. It means for every extra 1 in x, we predict that y will change by the slope. Meaning it increases by 6.086 grams. Part C, interpret the coefficient of determination of the least square regression line, r squared equals 0.819 in context. R squared represents what percent of the variation in x explains the variation in y. Make sure you use the word explain and not something else that implies causation. You can use other words instead of explain, such as accounted for or something like that. But as long as you use a word that does not imply causation. So definitely saying causes, that's bad. They say to interpret, so we can go straight into the explanation, and that says 0.819 in percent form is 81.9%. You can leave it as decimal or as percent. Traditionally, the majority of people, for whatever reason, write the r squared as a percent. 81.9% of the variation in y. I'm just going to put y in parentheses here so that you can follow what I'm doing. Can be explained by the variation in x. You can move it around if you don't like this passive voice. You can say that the variation in x explains r squared percent of the variation in y. But of course, we need context, so I'm going to erase the y and the x. I'm going to replace with verbal description of the variables and population. So y is the mass. And x is the length. 81.9% of the variation in mass in grams of bullfrogs can be explained by the variation in their length. All right, part D, consider the residuals of the 11 bullfrogs. The residuals are the y differences, the vertical distance from each point to the line. What is the length and mass of the bullfrog with the largest absolute value residual? So largest absolute value residual means the largest residual regardless of whether or not it's above or below the line. And it seems to be this point right here that has the largest residual. And they're asking what is the length and mass of that bullfrog. So the length is here and the mass is there. They want the largest absolute value residual. I'm going to write down that I marked the point with the largest absolute value residual. Why? So that if I mess up somewhere else, maybe I'll get some partial credit for finding it. Hashtag testing skills. Collect partial credit. And that bullfrog has length, looks like about 162, maybe? And mass of 355. Don't sweat if you cannot precisely estimate all of these values that fall between two values. Anything that's reasonable is fine. Part BII, does the least square regression line overestimate or underestimate the mass of the bullfrog identified in part BI? Well, the actual mass is here and the predicted mass is way up there, so it's an overestimation. So just say that. The least square regression line, it's okay to abbreviate as LSRL. Any abbreviation that is considered standard notation is fine. Non-standard is not fine. The least square regression line overestimates of that bullfrog because the line is above the point. I prefer to throw in numbers so it becomes obvious. Actual mass is approximately 355, and that's less than the predicted. The predicted mass looks like about 430. Moving on. Question 2. A dermatologist will conduct an experiment to investigate the effectiveness of a new drug to treat acne. The dermatologist has recruited 36 pairs of identical twins. Each person in the experiment has acne, and each person in the experiment will receive either the new drug or placebo. After each person in the experiment uses either the new drug or the placebo for 2 weeks, the dermatologist will evaluate the improvement in acne severity for each person on a scale from 0, no improvement, to 100 for complete cure. Identify the treatments, experimental units, and response variable. Well, the treatments are whatever you do to the people, right? So in this case, you either give them the new drug or you give them placebo. So those are the treatments. The new acne drug and the placebo. It may be a good thing to number them so that it's clear that you know that there are two things. An experiment unit is a single subject that you do things to in an experiment. And each single subject here is a person, so that's the one. Each person. And if you want to be more specific, each person in the 36 pairs of twins. The response variable in an experiment is the thing that you write down, the thing that you record as a result of the experiment. So in this case, it's the score from 0 to 100. Of the improvement in acne. Continuing on. Each twin in the experiment has a severity of acne similar to that of the other twin, but the severity of acne differs from one twin pair to another. But from one twin pair to the next, it could be more or less. Part B, for the dermatologist's experiment, describe a statistical advantage of using a matched pairs design where twins are paired rather than using a completely randomized design. By the way, they said describe a statistical advantage. That's pretty much, I'm pretty sure that means if you give one good advantage, you're fine. You don't need to keep going on. So I'm going to give you two. Advantages of using matched pairs. Of twins. One is because we're told that each pair of twins has similar severity and acne from each other. Then by picking matched pairs, you automatically get equal severity to start with. So you can directly compare. So direct comparison. Another advantage I can see that I'm going to write down here is that because they're twins, and in fact, we're told that they're identical twins, that means they're genetically identical. That saves us from having to worry about lurking variables in those genetics. So that means they give us control over that. Control over genetic factors. That may affect the results. Okay, moving on. For the dermatologist experiment, describe how the treatments can be randomly assigned to people using a matched pairs design in which twins are paired. So you have two twins and they're paired. So definitely you want one of them to have a treatment and you have the other to have the placebo. Random assignment means you're going to randomly decide which one gets the treatment and which one gets the placebo. And since there are two of them, it's a 50-50 chance. So anything that's 50-50 will work. So I'm going to flip a coin. Have one twin flip a coin, and let's say if it's heads, you win. If heads, that twin gets the treatment. If tails, then the other one wins. And now it gets a little tricky. A lot of students would stop here because this feels natural for you to think that, well, I've already decided who gets the treatment, so of course the other person gets the placebo. There's nothing as of course. Okay, if you want the other person to get the placebo, you have to say it. All right, now moving on to question 3. A machine at a manufacturing company is programmed to fill shampoo bottles such that the amount of shampoo in each bottle is normally distributed with a mean of 0.6 liter and standard deviation of 0.04. Let the random variable A represent the amount of shampoo in liters that is inserted into a bottle by the filling machine. The precision of a machine is pretty much a classic example used in all kinds of textbooks for the normal distribution. A bottle is considered to be underfilled if it has less than 0.5 liter of shampoo. Determine the probability that a randomly selected bottle of shampoo will be underfilled. So we have a normal distribution of the variable A, and it has a mean of 0.6 and a standard deviation of 0.04. And we're looking for underfilled bottle. So underfilled bottle have less than 0.5. So we're looking for this area. This area is the probability of being underfilled. So we'll just use our calculator for that. You have to identify the distribution by name and the parameters. And also that calculator speak doesn't count. However, recently I've seen some rubrics that are kind of permissive when it comes to calculator speak, but just because it has been permissive doesn't mean you should do it. So I'm going to use with normal, and it's okay to use capital N as an abbreviation for normal distribution because it's standard notation. To be more careful, I'm going to use the symbol with each number I'm using. Mu equals 0.60 and sigma equals 0.04. Then the probability I'm looking for, and the variable here is A, so I'm just going to use A, less than 0.5. This is usually what's required for a normal probability distribution. You need the cutoff and you need the direction. Show where it is that you're cutting off and show which side it is that you're computing. So once you've written this, you are home free. Just punch whatever in your calculator or use the table, do whatever method. And the answer is 0.0063. And they ask you a verbal question, you should give them a verbal answer. Sometimes it's not necessary, but get in a habit of doing it all the time anyway. After the bottles are filled, they are placed in boxes of 10 bottles per box. After the bottles are placed in the boxes, several boxes are placed in a crate for shipping to a beauty supply warehouse. The manufacturing company's contract with the beauty supply warehouse states that one box will be randomly selected from a crate. If 2 or more bottles in the selected box are underfilled, the entire crate will be rejected and sent back to the manufacturing company. Part B, the beauty supply warehouse manager is interested in the probability that a crate shipped to the warehouse will be rejected. Assume that the amounts of shampoo in the bottles are independent of each other. Part 1, define the random variable of interest for the warehouse manager and state how the random variable is distributed. So the random variable here is how many bottles are underfilled, because if I find 2 or more, then I'll reject the whole crate. By the way, I'm rejecting the whole crate, but I'm selecting only one box. So it only matters what the probability is in that box. How many boxes are there on a crate? It doesn't matter. So let's define our random variable. Let's give it a name. X of interest is the number underfilled bottles in a box of 10. And over here, they tell you that the shampoo bottles are independent and they're either underfilled or not underfilled. So that's a hint that says this should really be binomial. So let's go through the binomial conditions. Since each bottle is, number 1, independent, that's given. Number 2 is either underfilled or not. So that makes it binary. Number 3, well, independence means has a fixed probability of being underfilled of 0.0063. And number 4 is it out of a fixed total of 10. Therefore, we know that X is binomial. Part BII, determine the probability that a crate will be rejected. Well, a crate will be rejected if there are 2 or more. So probability crate rejected is the probability that X is greater than or equal to 2, where X is already defined in part I, so it's perfectly okay to use it. And X is a binomial distribution with n equals 10, p equals 0.0063. So I'm going to use technology. And depending on what kind of calculator you have, if you have the TI, it's a little tricky. You have to go 1 minus binom CDF. If you have the Casio, it's BCD. And if you have some sort of other technology, it may be simpler. So again, because they asked us a verbal question, we should give them a verbal answer. There. Continuing on with part C of question 3. To reduce the number of crates rejected by the beauty supply warehouse manager, the manufacturing company is considering adjusting the programming of the filling machines so that the amount of shampoo in each bottle is normally distributed with a mean of 0.56 and standard deviation of 0.03. Would you recommend that the manufacturing company use the original programming or the adjusted programming? Provide a statistical justification for your choice. We had a probability for the old settings, and now they are doing new settings. So the simplest thing to do is just redo the whole calculation. It may not be the fastest thing, but it is the simplest thing. In ports A and B. And with the new setting, I get 0.02275. With each bottle having a higher, it used to be 0.00 something, 0.0063, now it's 0.02. So with each bottle being more likely to be underfilled, then it's also more likely to have 2 or more underfilled bottles. So you could just stop the calculation here and explain all that verbally, but it's just simpler to just redo the binomial calculation as well. Then we get the probability that a crate is rejected is 0.0206. They asked a verbal question. Would you recommend something? Then we have to answer that verbal question. A higher chance of rejection. No, I would not recommend the new programming. Question 4. A survey conducted by a National Research Center asked a random sample of 920 teenagers in the United States how often they use a video streaming service. From the sample, 59% answered that they use a video streaming service every day. Construct and interpret a 95% confidence interval for the proportion of all teenagers in the United States who would respond that they use a video streaming service every day. This is a confidence interval question, so you know you're going to eventually have to write a conclusion in context. That means you need to say something verbally about the population, which in this case are teenagers, the sample, the 920 teenagers that were randomly selected, and the variable, and that is that they said that they use a video streaming service every day. So those kinds of verbal words should be in your answer somewhere. So first, I need to identify everything. This is something that your teacher may teach as a state stage. In a state stage, you define everything that you need to. If it were a hypothesis testing question, you get to the H0 and HA or H1. Population proportion. Of teens saying they use video streaming every day. Then we want 95% confidence interval of P where we're given that the sample proportion is 0.59. To do a confidence interval, you must always verify that the conditions for a confidence interval are met. Well, what are the conditions for CI of a proportion? You need a simple random sample. In this case, we're told it's random, so close enough. We need a sample that's less than 10% of the population as a rule of thumb, so that a sample without replacement could be treated as a sample with replacement. And in this case, yes, 920 is way less than 10% of all teenagers. And the third thing you need is at least 10 successes and 10 failures. And depending on the book, maybe you learn it as 5 successes and 5 failures, or you learn it as NP times 1 minus P, the whole thing is greater than or equal to 10. So depending on how you learned it, you do whatever it is that you were taught. In this case, they are met because 59% of 920 is way more than 10, and 41% of 920 is also way more than 10. So I'm going to say conditions for CI are met. 1, the sample is random. And how do I know? Because it's given in the problem. Number 2, the sample is independent. Let's say sample size n equals to 920 is less than 10% of all teens. So we can treat the sample as independent. So sample is independent. And we want at least 10 successes and 10 failures. Yes, because there are 59%, 0.59 times 920. That's 543, and that's greater than 10 successes. And then the rest of them, 920 minus 543, with 377, and that's greater than 10 failures. Alternatively, you could also be doing n times p times 1 minus p is greater than 10, and check that, and you calculate it out. It should be 222.548. That is greater than 10. So yeah, whichever way you are taught, just do that. And now that we have everything, we can compute. And the rule for the AP is you have to identify the method by formula or by name. If you want to identify by formula, you can scroll back up to the formula sheet and pretend to plug it in, even though in reality, we all know that you run the proportion confidence interval using your graphing calculator. I'm just going to identify it by name using the one sample proportion with the Z distribution. Z is a standard notation for standard normal distribution, so you don't have to explain it. Then you get the result. Once you get the numerical answer, you should write your verbal conclusion in context. And the verbal conclusion in context would include the variable and the population described verbally. By the way, this is necessary. On the AP, when you do inferential statistics, you want to make sure you say words that show us that you understand that your conclusion is not certain. There's a degree of uncertainty in doing inferential statistics. So words like we are 95% confident is important. You don't have that, you lose points. There are people who are even more strict than this, and they demand that you say something about your being confident about the interval, not about the population proportion, because the population proportion is what it is. The AP has never been that strict. Neither have I. All right. Based on the confidence interval in part A, do the sample data provide convincing statistical evidence that the proportion of all teenagers in the United States who would respond that they use a video streaming service every day is not 0.5? Justify your answer. All right, so here's the p-axis. And we're saying that, can we be sure that it's not 0.5 based on the confidence interval? The confidence interval goes from 558 to 0.622. So we're 95% confident that P is in there somewhere. Well, if it's in there, then it cannot be where 0.5 is, right? Because 0.5 is out here. So yeah, just say that. Do the sample provide convincing? Okay, so the answer is yes. Since the CI is completely above 0.5, and then just copy down this stuff. The sample data. Convincing evidence. If you want to add on the confidence level, and yeah, just copy down the rest of the question prompt. You know what? I'm going to add on something here. So I'm going to add on here. 0.5 is not plausible. My AT teacher friend told me that the word plausible has been becoming something of a buzzword in the AP Stats world. All right, we're now on question 5. Studies have shown that foods rich in compounds known as, I have no idea how to say that, flavonoids, help lower blood pressure. Researchers conducted a study to investigate whether there was a greater reduction in blood pressure for people who consumed dark chocolate, which contains flavonoids, than people who consumed white chocolate, which does not contain flavonoids. White chocolate is just oil and sugar. It's not even chocolate. 25 healthy adults agreed to participate in the study and add 3.5 ounces of chocolate to their daily diets. Of the 25 participants, 13 were randomly assigned to the dark chocolate group and the rest were assigned to the white chocolate group. All participants had their blood pressure recorded in millimeters of mercury before adding chocolate to their daily diets, and again 30 days after adding chocolate to their daily diets. The reduction in blood pressure before minus after. So that means if there's a reduction, then before minus after would be a positive number. We prefer to have larger differences. We prefer to have positive differences. For each of the participants in the two groups is shown in the dot plots below. So there's a dot plot for dark chocolate and there's a dot plot for white chocolate. A, determine and compare the medians of the reduction in blood pressure for two groups. A median is the dot that's in the middle. So just count toward the middle. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 6, 6. So here's the median. White chocolate. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So the median is in between the last two. So the median is here. For dark chocolate, median is equal to, looks like 7. For dark chocolate, median equals 7. For white chocolate, median equals 0. All right, so I already did the determine part, so I still have to do the compare part. Has higher median, and then whatever the variable is, reduction in blood pressure. Then white chocolate. Continuing, the researchers found the mean reduction in blood pressure for those who consumed dark chocolate is X bar subscript dark is equal to 6.08 millimeters mercury. And the mean reduction in blood pressure for those who consumed white chocolate is X bar subscript white equals 0.42 millimeters mercury. Part B, one researcher indicated that because the difference in sample mean of 0.66 is greater than 0, so the difference between 6.08 and 0.42 is 5.66 is greater than 0, there is convincing statistical evidence to conclude that the population mean blood pressure reduction for those who consume dark chocolate is greater than for those who consume white chocolate. So here's a researcher who looks at a sample, finds that the mean of that sample, the sample of the differences, find that the mean of that sample is 5.66 and says, well, you know what, 5.66 is positive, therefore I conclude that it is for sure positive. So there's a mistake between sample and population mean. So the mistake is going directly from the sample mean to the population mean. And so we know that's wrong. And the question prompt is, why might the researcher's conclusion based only on the difference in sample means of 5.66 not necessarily be true? So we know it's wrong. We just have to explain why it's wrong. It's wrong because you really, if you want to go from sample to population, you have to do inferential statistics. You cannot just look at the sample statistic and say that that's true of the population. So here's the idea. You have 5.66, and let's say there's 0, and you say, well, because my mean is 5.66, therefore the population mean is probably around here somewhere, near the 5.66. Well, yeah, but it could also be near over here, right? Well, we can only know for sure that it's far away enough from 0 if the graph is something like this, where, yeah, unlikely that the mean is down there because, yeah, it's kind of hard to get 5.66 out of that. That's the idea of p-value. So you use what you understand of the idea of p-value, and then you apply it to this case. So if the situation like that, then yeah, the conclusion is probably correct. But the situation could also be like this, where 5.66 is here, 0 is here, but the curve is very spread out. So the mean could be negative. It could be very easy to get to 5.66. The mean difference of 5.66 is only from a sample. Not population. If you stop right there, I'm pretty sure you get some partial credit. But I'm going to put in more details. I'm going to basically explain p-value and how it works with sampling distribution. Without knowing the spread of the difference means, there could be a high probability of getting 5.66 anyway. I'm underlining sample and population because I'm pretty sure that by itself would get me some partial credit. And then the rest of it is basically I'm explaining how p-value works. All right, let's continue on. A simulation was conducted to investigate whether there is a greater reduction of blood pressure from those who consume dark chocolate than for those who consume white chocolate. The simulation was conducted under the assumption that no difference exists. The results of 120 trials of the simulation are shown in the following dot plot. So this is a little tricky. First time I read it wrong. And then I realized that, well, this is a statistics test, so any simulation would be a statistic simulation and not some sort of biological simulation. All these dot plots represent simulated differences in mean. So each of these dots already represent a difference in a sample of 25 people. Use results of simulation to determine whether the results from the 25 participants in the study provide convincing statistical evidence at a 5% level of significance. Right, so all of this stuff tells us that they are looking for a hypothesis test with alpha equals 0.05. That adding dark chocolate to a daily diet will result in a greater reduction in blood pressure on average than adding white chocolate to a daily diet. Justify your answer. So this is a hypothesis testing problem, so we need to write the hypotheses. We're going to define our parameter. Mu is a population mean difference in blood pressure. And since it's a difference, we need to define which way we're subtracting, right? So according to this, it's dark chocolate subtract white chocolate. Then we're testing H0 mu equals 0 against HA or H1. Mu is positive at alpha equals 0.05. And given that X bar is equal to 5.66, that's the information we're given in part B. To do this hypothesis test, we need a p-value. But we can't do a p-value the usual way, because even though we have a sample mean, we don't have the sample standard deviation, and we are looking at this sampling distribution, a simulated sampling distribution, and we don't see that the conditions for the usual tests with the t-distribution would work. So now we need to somehow find a p-value based on the simulation itself. Those of you who have done the smelling Parkinson's activity by Doug Tyson, you would know exactly what to do now. So thank you, Doug Tyson. But it involves applying the definition of the p-value itself. So let me walk you through that. P-value is defined as the probability of getting a sample statistic that's at least as extreme as the observed sample statistic, assuming H0 is true. Well, in this case, we have a simulation that was conducted under the assumption that no difference exists, which is what H0 says. H0 says the difference in means is 0. It's the difference in mean, right? The mean of the difference is 0. So yes, we have that part. So what about the rest of it? At least as extreme as, because HA is a white-tail test, at least as extreme as means at least as large as, greater than or equal. As the observed sample, what is the observed sample statistic? The observed sample statistic is X bar equals 5.66. So the simulation that we're given assumes that H0 is true, so we can look at the simulation to figure out the probability we're looking for, the probability of greater than or equal to 5.66. Well, 5.66 is here. So the probability of being greater than or equal to that is the probability of these 3 dots. And that probability is 3 dots out of 120. That is the p-value. All right, so in this case, this is the probability of getting a sample stat. What kind of sample stat are we looking at? An X bar. And by the way, this is the graph. This is the simulation graph of X bar. So of getting X bar that at least as extreme as that's greater than or equal the observed stat, that's 5.66 right here. Assuming H0 is true, and that is what the simulation does. So it's the probability of getting X bar that's greater than or equal to 5.66 in the simulation. Therefore, p-value is equal to 3 out of 120, which in decimal form is 0.025, 1 out of 40. And that is less than alpha equals 0.05. So we get to reject H0. So now we're in familiar territory. Once you reject H0, you just write your verbal conclusion in context the usual way. There is sufficient evidence to support the claim that that adding dark chocolate, all of this stuff. That adding dark chocolate will result in greater reduction of blood pressure than white chocolate. There we go. Now moving on to question 6. To compare success rates for treating allergies at 2 clinics that specialize in treating allergy sufferers, researchers selected random samples of patient records from the 2 clinics. The following table summarizes the data. Okay. Part AI, complete the following table by recording the relative frequencies of successful and unsuccessful treatments at each clinic. That means they're looking for relative frequencies in clinic A separately from the relative frequencies in clinic B. They want all of this to add up to 100% and all of that to add up to 100% separately. So that means we're going to divide by the column total. So in the A column, we're dividing by 139, and in the B column, we'll divide by 68. So this would be 51 over 139. That's 0.367, and this is 0.633. And over here would be 33 divided by 68. Based on the relative frequency table, which clinic is more successful in treating allergy sufferers? So overall, it looks like A is more successful because it's got a higher success rate. It's 0.633. Which is higher than B's rate. B's rate is only 0.515. Okay, continuing on. Based on the design of the study, would a statistically significant result allow the researchers to conclude that receiving treatments at the clinic you selected in part AII, that will be clinic A, causes, oh, yeah, you see this, and that would be a keyword. Because some studies allow you to prove causation and other studies don't. So when they say causes, you have to trigger in your mind that ooh, to actually say causation, we need something special. Causes a higher percentage of successful treatments than at other clinics. Well, let's see if this is the kind of study that would allow us to have causation. What did the researchers do? They selected random samples of patient records. All they did was to go in and ask to see copies of files. They copy the files, they copy down number of successful treatments and a number of unsuccessful treatments. It's an observational study, and more specifically, it's a cross-sectional observational study. And as far as we know, in first-year statistics, observational studies do not lead to causation. In first-year statistics, the only way to prove causation is to do a randomized controlled experiment. And that's not what's happening here, so that would be our answer. Would this allow the researcher to conclude that? So the answer is no, it would not. The researchers only did a cross-sectional observational study. Which, without more, cannot prove causation. Period. When we're in first-year statistics, we only know one way of proving causation, and this isn't it. Continuing on, a physician who worked at both clinics believed that it was important to separate the patients in the study by severity of the patient's allergy, either severe or mild. The physician constructed the following mosaic plot. The values in the mosaic plot represent the number of patients who were either successfully treated or unsuccessfully treated in each allergy severity group within each clinic. For example, the value 78 represents the number of patients successfully treated in the mild group within Clinic A. So this whole graph is part of Clinic A. This number 78 is for mild allergy, and it's dark color, so that represents success. Light color represents non-success, and over here is mild, severe, and all of the left graph is Clinic A, and all of the right graph is Clinic B. Based on the mosaic plot, the physician concluded the following. For mild allergy sufferers, Clinic B was more successful. Yes, because for Clinic B, the success rate is somewhere above 90%, and for Clinic A, somewhere below 80%. So yes, that's true. For severe allergy sufferers, so for the blocks on the right, this white block and that white block, Clinic B was also more successful because its success rate is above 40%, and Clinic A success rate is below 40%. So yep, Clinic B is better than A in both types of allergies. Now question CI. For each clinic, which allergy severity is treated more successfully? For Clinic A, it's better at treating mild because mild has a higher success rate than severe. Justify your answer because the left block is taller than the right block. If I were in my own class, I would just refer to the graph. This is higher than that. But since in a written exam, I don't know how the rubric works. Going by numbers is always the safer route. So because the mild success rate is 78 over 78 plus 26. And that works out to 0.75, whereas the severe success rate is 10 out of 35, which is 0.286. Clinic B, also mild. Again, because the block on the left is taller than the block on the right, but also again, because in a written exam, working out the number is always safer. 11 out of 12. In decimal form is 0.916. Whereas for severe is 24 out of, looks like 56. Which is 0.429. Continuing, for each clinic, which allergy severity is more likely to be treated? So which allergy severity is more likely to show up at the door? Well, for clinic A, we got this many mild cases and that many severe cases. So this looks like 104, and this is 35. So for clinic A, they got 104 cases, which is more than 35 cases for severe. Whereas for clinic B, they treat more severe cases. They treat 56 severe cases compared to just 12 mild. Now, part B, using the answers from part C, give a reasonable explanation of why the more successful clinic identified in part A is the same as or different from the physician's conclusion that clinic B is more successful in treating both severe and mild allergies. So let's go back and look at question AII to even see what they're even asking. So over here, the physicians conclude that clinic B is better than clinic A in every way, in the mild cases and in the severe cases. But back in part AII, we concluded that clinic A is more successful in treating allergy. That's a contradiction. Based on these numbers in the overall operation, we conclude that clinic A is more successful. But when the physician broke down into different types of allergies, then the numbers also show that clinic B is more successful in each type. How can it be that clinic B is better than A in every single category, but when you lump them all together, A comes out ahead? And they tell us that we should be looking at part C for the answer. Part C I says both clinics are really good at treating mild cancer. But clinic A gets to treat the mild cancer, which is what they're good at, whereas clinic B ended up treating a lot of severe, sorry, not cancer, but allergies, which they're not good at. Okay, there we go. That's the explanation. Both clinics are better at treating mild allergies. But clinic B have to treat more severe allergies, severe allergy cases, while clinic A gets to treat more cases of mild. So in other words, A gets to play to its strength, whereas B had to play to its weakness. Thus, even though B is more successful than A in each type of allergies, overall, A came out ahead. So that's my statistical explanation of what's going on. This is a phenomenon known as Simpson's paradox. And this can also be explained algebraically. And that is because when you look at the mild success rate, it's a different denominator. When you look at the severe success rate, it's a different denominator. But when you put them together, you don't get to just add the denominators straight. You have to do common denominator, and that causes things to go haywire, go out of whack, and Simpson paradox happens. So yeah, there's an algebraic explanation and there's a statistical explanation, and what I'm giving is a statistical explanation. All right, that was a lot of fun. I hope this helps. If you have any questions or comments, or if you're wondering something, or if you have any feedback, please put in the comments. Like, share, and subscribe for more content. And thanks for watching. Bye.